because it's very tedious. Yeah. What I like to say is you have to leverage on all the analysis tool offered by the Vitis tool. Yeah, because it's not just a kernel optimization. Actually, provide very handy tools to analyze the whole systems, and it provides the actual runtime data. Yeah, and based on the data, you can induce very useful information and guide you for the optimization directions. Yeah. So in here, I only highlight few things. Yeah. So whenever the student came to me, say something wrong, he could not make it work, or performance is really bad, and actually all the information is in the log file. You need to know what to look for this information and learn how to interpret those data. Yeah, and that's a very important thing to learn. Yeah. Okay. Yeah. So that's the topics we will talk about. I hope I can finish by 9 p.m. Okay. This programming model we already introduced, so I won't address. Yeah. Okay. In here, in the Vitis, there are two target flow. Okay. One is the IP flow. One is the kernel flow, Vitis kernel flow or Vivado IP flow. Vivado IP flow simply give you an IP, generate an IP. So for those interface, it doesn't, the IP generate only intend to communicate for later integration with other kernel. Okay, it doesn't address communicate with the host. Okay, if you develop a kernel function and that kernel function gonna to interface with your host program, in that case, you need to use a Vitis kernel flow. Okay. So for Vitis kernel flow, there are two things. One is the module block. Okay. So for block, in the later lecture, I will introduce the I/O interface. I will talk much more detail. In here, just give you an idea. For the Vitis kernel flow, you design a kernel function. So this kernel function or the block has a block level protocol. Block level protocol is used to communicate with host. This one is to communicate with host. Okay, it provides three communication scheme. One is the sequential mode. During the handshake, you start the kernel, and then it finish, it tells you done. Okay, remember in the pink, we talk about the start and done interface. Yeah, that's a handshake. Or you can run the kernel in pipeline mode. The pipeline mode means before the kernel finish, you can enqueue next command. Prepare next data buffer, for example. So once the kernel finish, then the data can come in. Or the kernel, if the kernel has the multiple kernel and execute step by step, so you can run this block in pipeline fashion. Then you use this interface protocol or free running one. That's the most simple one. Yeah. So that's the block level protocol. And for the data pool, you have a three interface that also we talk about in the lab 2, yeah, the pink lecture. So you have a XI light, that's for the argument or some small amount of interface argument data. You can use XI like, or you can use XI master, or you can use XI as the streaming. Okay, yeah. So for data pool interface protocol, use these three, and for the whole kernel function control, you use these three types. Yeah. So this is the kernel flow development target. Yeah. And in most of our lab, we are doing this. Yeah, we design a simple kernel function and then we communicate with the host. So mostly we deal with this. However, when you develop a bigger system, then it has a lot of IP. Yeah, and then for each IP you want to verify individual IP. You use the IP flow, and the IP later on will integrate into a chip level, and then communicate with the host. Yeah. So yeah, just let you understand, distinguish this target flow. Okay. This is a little bit tedious in this one. Okay. Basically, introduce. We have two platforms. One is U50. It's a PCIe accelerator card. And this PCIe accelerator card mostly used in the data centers. And we also have the pink. So this is an embedded platform. So you all learn these two systems. So in here, for the PCIe, so you have a host program. Your host program compile with the GCC compiler. You generate the host executable. And you have a kernel, and the kernel could compose by RTL code. Or you have a CC++. The C++ code, you can generate the kernel module either through the Vitis AAHLS or using the Vitis compiler. Okay, and you all learn this too. Yeah, we have a Vivado AAHLS, a Vitis AAHLS, and you also install the Vitis too. Yeah, so the same kernel function, the C code, you can run through the AAHLS and you explore IP and package, or you use run the Vitis, generate the package, and then you link together and generate the XCL bin file. That's the bitstream file. So to execute that, you simply run this function. This is an argument. That's a program file. Actually, if we look at the lab code, that's a program file. That's an argument pit. Yeah, he loaded and then generally go to the OpenCL flow. And for the embedded, and in here we all use XRT. Okay, yeah. Actually, for embedded system, we did not run with XRT. We use a pink. Pink is a much simple embedded system, and XRT that is much more capable. It's a module OS kernels. Yeah. So to run like a pink Z2 board could not run XRT. That's a very small devices. To run the XRT, you need like a 102, 104, 106 FPGA, and this FPGA cost like a 2,000, around 2,000 US dollar the board. Yeah, for this level of FPGA, you can run XRT. But we are talking about like this FPGA, the board like only 100 US dollars. Yeah, so very, very low cost edge device. And for this device, you cannot support XRT. Yeah. Okay, so so in here, the difference between the data center flow and embedded is first the the host program is running on the SoC part of the FPGA. So it's run on the ARM processor. Okay. And the kernel function is the same. The kernel function, and for Vitis AI, for the embedded, it offers the AI engine. Yeah. However, the kernel function development flow is the same. Same as the embedded and the data center. The flow is the same. So we generate the XCL bin. And for the host program, they compile with the ARM C++ compiler. It generates the host year file, and it has a one actual step here. Okay, that it will integrate, package, and generate the boot bin file, and save it in the SD card. So when you boot, then it will has the right kernel function library built into the OS kernels. Yeah, and then when you SQ, you SQ with this code. In here, the difference is in here that for embedded system, you generate the boot bin file, so that you will boot with a new kernel. However, we didn't really exercise this flow. Yeah. Instead, we use pink for very small edge device. Okay, the following is my recommendation. Yeah. First, when we do the application acceleration, yeah, we have to pay attention to the system level optimization, which include the system resource and performance. The system resource here, mainly the FPGA resource. Okay, with the given, because FPGA device has is a fixed capacities, so we need to have a resource fit into the FPGA capacity. And normally we start with the kernel optimization. Okay, and then actually the kernel partition and kernel optimization really depend on how the host program communicate with kernel. So actually these two quite yeah, interconnected. Yeah. And then you also need to pay a lot of attention on the data transfer optimization. Yeah, because the data transfer is across I/O bus. I/O bus always has a limited bandwidth. Also, I/O bus take a longer latency. Yeah. For this reason, often the data transfer is the bottleneck in the whole system. Yeah. So in here, I simply want to emphasize that not just the kernel optimization, there are many other factors we have to pay attention to in order to give you a real speed up on the whole application. So in here, that's why to do the host optimization or system performance analysis, you really need a lot of tools to do system level analysis. Yeah, so that you will know the directions. Because in the system, there are so many factors happen, and those factors interact each other. So there always a trade-off. When you optimize this one, and often you hurt the other one. Yeah. So you have to consider the whole thing together. You cannot be too simple-minded. Yeah. Then you will never be able to get a good balanced system. Okay. So in here, that's the AAHLS development flow. Okay, we do the AAHLS. We have two tools. We have a Vitis AAHLS, and we have a Vitis. Okay, this Vitis AAHLS is simply doing the kernel function. Okay, and Vitis 2 give you more of a system level. Okay. But we start with the Vitis HLS to do the kernel optimization. And if you, I believe you all have run the Vitis HLS. First, we need to do in here. Actually, the example we are running are very simple example, so you don't see the benefit of the profiling tool. However, in the later project, like the Lab C or final projects, they are much more complicated. I believe you will need the profiling tool to give you better judgment. Yeah. Okay. And then the HLS, you go through this threefold. Okay. First, you have to run C simulation. Okay. Make sure it's functional correctly. And then you proceed to the synthesis. And in the synthesis, you use the directive pragma to guide the HLS optimization process. And I would recommend not to change your C code unless there are certain dependency. You have to restructure the code. And if the pragma can do the work for you, use the pragma. Okay, don't change your C code because that will provide portability. Yeah. Once you change your C code, just like you do the RTL design, and that's a fixed one. This is fixed hardware. Then you cannot do the future the adaptation. And in the synthesis, I strongly recommend you have to detail to study the synthesis summary report, and you use leverage the schedules viewer, property viewer, and data flow viewer to analyze your data path and the control flow, especially the schedule viewer. You will see how many cycles it takes, and for each cycle, you will see what kind of work done in this cycle. Yeah, and that also schedule viewer also cross reference to your source code. Okay, so by doing this way, you know the source code behavior and how it affects the latency. Yeah. So that's a very handy tool. So use it often. And then CRT Across Simulation. Okay, and certain things, especially you are using stream interface, stream, we use that stream interface a lot because the stream is much efficient and higher performance. Because streaming is a data flow architecture, it's a higher performance and use much less resource. And those stream behavior often you could not find the problem in the C simulation. C simulation all run correctly, but when you do often you will run into a hand, the simulation hand. Simply because the stream using the FIFO underrun or overrun. Those are situations that you will not observe in C simulation, but you have to debug in the CRT code simulation. And it provides this tool, the waveform viewer, and there is a deadlock viewer. Deadlock viewer basically lets you to analyze the FIFO depth of each stage. So you can analyze and see whether it happened overflow or underflow. Okay, so do follow this step. Don't skip any one of them. Some people say, "Oh, C simulation work, and I got a synthesis, and then I skip this one. And then I just simply integrate and run in the FPGA." Yeah, once it's in the FPGA, you got much less tool to do the analysis because it's running in the actual hardware. You cannot look at the inside the waveform behavior. Yeah, and it will be extremely difficult to debug in system. And CRT code simulation give you very it's very close to actual hardware, but not exactly. Not exactly. I will introduce something the CRT code simulation could not model the actual hardware. Yeah, but that's the limited cases. Yeah. Okay. So my recommendation in the Vitis HLS, go through step by step, see simulation synthesis and coding. Always run coding. I know some people just skip because coding run much slower. Okay, and then let's go back, go to the Vitis flow. Okay, Vitis it also has it has a software emulation. Okay, for software emulation, the host program and peer the kernel is just a native compiler run in the host machine. Okay, yeah, and the source level debugging. So we can leverage a lot of source level debugging tool. So running system debugging is quite convenient. Yeah. And then we start doing the hardware emulation. That's the coding. This is the CRT coding, like the Vitis HLS. Yeah. In this case, the host program is run in the x86, natively compiled into the x86 executable. And kernel code actually compiled into an RTL is run in the simulator. So you will see the hardware emulation is you have the C code actually compiled to executable. And then you have the RTL, actually it's running in the simulator. Okay. And this one, the communication, that's the test bench. To communicate these two, the Vitis create some middleware program, some intermediate, or you can say the some bench code here. Okay. And for this kind of simulation, it cannot be too fine grained. It cannot be too fine grained. Down to single level. Okay, so normally it has to do the batch run. Okay, so there's a certain limitation on this kind of code simulation due to the simulation model issue. Okay. However, since this part, your kernel function is run in the actual hardware, although through the simulator, but it gives you cycle accurate view. Okay, so the kernel function is say how many cycles you run, and in the actual hardware, exactly same number of the cycle. So it gives you very good performance estimation. Yeah. However, certain issue in hardware will not be reproduced in the hardware emulation. Yeah. And sometimes, like the PCIe, it uses a functional model. It does not have the actual hardware. So it does not reflect the actual PCIe bandwidth and hardware. And for DRAM access, it doesn't use the actual DRAM. The DRAM is a functional model too, so it does not model the latency, the actual DRAM latency. So for the performance related to the I/O PCIe transfer or related to the external global memory access, those cycle count is not accurate. But the kernel function inside is cycle accurate. Yeah, you must understand this. Yeah, you know, yeah, something you can trust, something you cannot trust. So this is the hardware emulation. And for hardware, you actually running in the FPGA. The kernel code actually compile into the FPGA bitstream and run in the actual FPGA. Yeah. So this is everything is accurate. Okay. So it reflects the actual performance of your accelerated application. Yeah. And so to do the system level performance, you have to run. If you really want to look at your whole application performance, you have to look at in the hardware mode. That means you run actual FPGA. When you run the actual FPGA, you have to do the profiling. The XRT provide a lot of facilities that it can record, profile a lot of useful data, timing data, and used for later analysis. And I will introduce that later. So you profile the data from the actual hardware run, and then yeah, you can optimize system performance. And but remember, when this device is really put into the production, you have to turn off the profile. Otherwise, it actually generates a lot of overhead. Yeah. Okay. So for profiling tool, you can use the profiling in hardware emulation and hardware mode. The system emulation, you don't do the profiling. Yeah. Because system emulation, everything is fake. It's not real hardware, so the profiling doesn't make sense. Yeah. So when you do the profiling, you will get the host and device, the timeline event. And you can also see the API calling sequence. So in the runtime, the API, yeah, the sequence of API calling, yeah, you can know. Yeah. And the kernel execution sequence and the duration, you will see the duration and its sequence. And the kernel start and stop signal. And you can also see the PCIe or XI transactions. You can look at all the data traffic. You can see how much time it takes to transfer the data. You can also see if the memory, for example, the memory is used by multiple kernel. Then you can see how much share this kernel for use the DRAM bus. Yeah, because DRAM shared by multiple kernel. Yeah. And you can observe when you write the kernel function, you access memory. And due to the coding style problem, you may not use actual XI burst, maybe single transfer. Then you give you an idea when the request issue and how much time later the data actually return. You can also see that the DRAM data bus utilization. For example, mostly if you don't take care of the pipeline or burst correctly, you may only use the DRAM maybe only 10% of a DRAM bus utilization. Yeah, or even 5%. Yeah, because you do single transfer. For example, for these things, a lot of things need to optimize. Yeah, and the profiling give you the insight. Often you don't see that from your source code. Yeah, it simply has to look at the actual system waveform to observe that. Yeah. So user event and range profiling. Yeah. So the profiling give you a lot of important information. Another Vitis offer very powerful tool, Vitis analyzer. Okay, it offers the following information. First is the guidance. Yeah, remember the Xilinx HLS has been in industry for many years. I think maybe 2 decades. So in this process, it accumulate a lot of system design experience and how people make mistakes. So he compile into a guidance report. Oh. And this guidance report I don't see in 2019.2, the previous Vitis tool we use. It's available in 2020.2. Yeah, maybe 2020.1 doesn't have that. I didn't try. Yeah, the 2020.2 a lot of improvement down in here. So you also provide the guidance. So the guidance you will show your application where is not suboptimal, and you will provide actionable feedback. It will suggest you how you should write your code, how you should use the pragma. Yeah, it will suggest how to improve it. So you can see that's basically a role of a mentor. Yeah, you have a problem, you go ask the mentor, but the guidance give you suggestion how you can improve it. Yeah, so it's very useful. Yeah, and the profile summary, there's a annotated detail for overall application performance, and you can look at the actual application timeline. So we should use that oftenly. So in the future, when you are doing any presentation to show your performance, I expect you provide the application timeline. You use the application timeline to explain the system behavior. Yeah, and really study the application timeline carefully. Yeah, and you can change the host program, and then you can observe how the application timeline change, how the whole latency get improved. Yeah, you iterate this process that give you a lot of insight. Yeah, the HLS report that give you a guidance for the kernel optimization. Yeah, if you're really a hardware guy and want to see the detailed waveform, it also provide a waveform view and viewer. Yeah, then you can really spot the performance bottlenecks. Yeah. So let's look at this report. For example, the guidance. Okay, it provide information about some violation, and it will give you a suggested resolution, and also a web link for detailed description. Yeah, and the guidance has a different level of guidance, and then the guidance report is generated at each level of the tool is running. Okay, and the profile summary report. Yeah, yeah, it gives you the kernel execution, top kernel execution, each compute unit utilization or data transfer. It gives you those profiles. Yeah. Also, it has a lot of information. Application timeline. Yeah. Okay. So for each the host code, the API, it shows the function SQ where is the data transfer. Yeah, you can see the kernel execution sequence. Yeah, so you see how the host program and kernel function interact with each other, and also with the data buffer. And the duration of the data buffer is pretty accurate, because in the kernel function, in the XRT, it keep track all the event with a timestamp. So the duration is pretty accurate. Yeah. The HLS report, yeah, it gives you each kernel function, the latency, and the iteration, one iteration latency, and whether it's pipeline, yeah, and the resource usage of each function. Yeah. So it has a very rich information here. Okay, there's a waveform viewer. Yeah. So you can see the address in the waveform viewer. You can see it does the data access. You can even know what the data. By looking at the address, you will know which part of a kernel is doing this transfer. For example, you have a lot of PE, a lot of kernel functions. Then by looking at the address, you can identify which kernel function is doing the data access. Yeah. So it gives you good information too. Yeah. Okay. Yeah. And also, I strongly recommend you really want to review the log file. Okay. A lot of time, you find out something wrong. The first resource to find is look at the log file. Yeah, because the log file print out a lot of very comprehensive information during the whole optimization process. Yeah, if anything wrong, you will print out the message. Yeah, and also from the log file, you get better understanding how the optimization process is doing. So for C simulation, synthesis, or CRT Across Simulation, they all generate very rich log file. For example, I list the following. During the synthesis, we can look at here. During the synthesis, in the synthesis step, a lot of status and optimization. For example, okay, it shows a start conversion resource file into memory. Interface detection, yeah, that's a step of a process. You will see what it does the bus rewrite access for the port. Yeah. And then compiler transform code into the operation. Yeah. Let's see tripcom automatic pipeline. You will see whether it does the automatic pipeline. In here, from this log message, you see these two doing the automatic pipeline of the loop. So thus it says, even though for this loop I didn't use the pragma pipeline, the tool will do the automatic pipeline for you. And this doesn't happen before. In the 2019 version, I don't see it do the automatic pipeline. But the new version, it does the new pipeline. Yeah. And sometimes doing the enrolling loop automatically or user directed. Yeah. So when you look at the code and the synthesis report, you find out, I didn't use any enrolling. Why the result or from the timeline? It seems that does the parallelism more than you can expect. Because the tool is so smart that it does the automatic enrolling. But sometimes it may use too much resource, then you really don't want it does the automatic enrolling. Yeah. So you must know what the tool does. Yeah. Okay. And you will also see balance expression. Yeah. And okay, it seems that it does the loop flattering automatically. Yeah. And you will print out more detailed information which loop it does the loop flattering. Yeah. And it find out partial right detection. Yeah, that's important. And oh, I remember a team work on the RISC-V processor, and then it find out the pipeline could not achieve II equal 1, and we spent a lot of time to find out that during the write back is partial write. For example, the data memory is a 4-byte memory, and the read file only write 1 byte, and this memory doesn't provide you with the byte enable, for example. It doesn't use you cannot write 1 byte. So in order to write 1 byte, into a 4-byte with memory. How can you do that? You have to read, modify, and write, right? You have to read the data out and modify that 1 byte and write back again. So this partial write could not achieve in 1 cycle. It takes 2 cycles. Read out, modify, and write back. It takes 2 cycles. So that explains that the pipeline could not achieve II equal 1. Yeah. So in that case, spend a lot of time to figure out what happened, why II could not doing 1. But if he carefully study the census log file, definitely you will find out it detects there's a partial write. So you will find out the reason why II could not achieve 1. Yeah. So what I'm saying is, really, if anything wrong, go back to read the log file first. That's a very good practice. Yeah. That review a lot of information in the log file. Okay. Review log file. That's my advice. Okay, guideline for writing a test bench. Okay. First, I would suggest you always separate the top function for census from the test bench. You separate these 2 files. Yeah. And if there are multiple kernel functions, yeah, and group them in one top function for synthesis, it provides a much better optimization. Yeah. So the test bench should execute top level function for multiple transactions. Okay. So in here, that's the test coverage. Yeah. When we develop a kernel function, and we also develop the host program to validate the kernel function, but make sure the simulation, C simulation and co-sim, you use enough data coverage to provide good test coverage. Yeah, make sure every part of the kernel function is exercised. If the kernel function has if else have a branch condition, make sure each branch get tested with the test data you provide. Yeah. So for those doing software program, one way to validate the quality of application is to look at the test coverage report. Test coverage report give you analyze each branch or each line of the source code, whether it get exercised by the test data you provide. Yeah. So make sure you provide the test data that could exercise every branch of your code to make sure the test coverage is enough. Yeah, that's an important thing. Okay, you use the same test bench for C simulation and for the code simulation. Yeah. Okay, so if I want to estimate the performance for the as I said in the code simulation, the kernel function is run actual hardware with cycle accurate. Yeah, and you want to estimate its latency for performance. But make sure you do have the right data, test data, to exercise every branch of your code so that you have an overall, because for a kernel function, it's not a fixed latency. It's also data dependent. For certain data, it may have a shorter latency. For other data, it may have a longer latency. In this case, make sure you provide the test data to cover all the possible latency. Yeah. By doing that, it gives you a better idea. And also, it gives you, if you do provide enough test data, then it gives you good enough average latency. Yeah. that then in the system level performance, you won't run into a surprise. Yeah. Okay. And for the host test program, you always check the correctness of the return value. And the good practice is result is correct, you return 0. And result is incorrect, you return non-zero value. And also, you have a different value to indicate the error type. Remember, when you execute that, you have a host program, and you run the FPGA. And then when in the system running, okay, maybe run a few hours and then it's error. And then you find out the data is not correct. But if you only return 0 or non-zero, there's no way for you to tell what is the source of error. Yeah. So you can always return a value, different value to indicate different error type. So it's give you a better handle for debugging. Otherwise, you have no information to judge what the problem. And then you want to rerun it again, maybe it may not happen again, right? Or it take even longer time to duplicate. Yeah. So yeah, keep this good practice. Yeah, use a different value indicate the different error type. Okay, this is the last slide. The CRT code simulation. Okay, as I said, for CRT code simulation, there are 3 phases. The first phase is run C simulation on the host program. That's the phase 1. And the host program simply to prepare the test bench data. Okay, prepare the input vector to the kernel function. And the second phase is running the simulation. So running the simulation, it has all the input test data comes in. Yeah, and then you generate the output. And phase 3, the simulation, it goes back to the host program again. It takes the return data from the kernel function and do the result checking. Yeah. In here, do pay attention that for this kernel function, if it's work on a frame, a data frame, for example, work on a data frame, then you need to provide the whole data frame data. Yeah. But we all know this kernel function, when you put into system, the data actually at the runtime feed in 1 by 1, right? Yeah. For example, there's a HDMI input. The data feed in as a string. Okay, and then the kernel execute each data, string data, 1 by 1. That's the actual hardware. But for doing the coding, you cannot do this fine-grained iteration because it will be too slow. Yeah, I remember in lab 2, you have a discussion that the stream, the FIFO depth, yeah. So Herton has I think it's Herton, right? Yeah, you have a clever way that you code each kernel function, but just provide one data set.
Oh, yes.
Yeah, that's I have to say it's a smart way, yeah, to do that to solve the problem, yeah, and yeah, but as you know, the simulation will be run very slow because it has to always do for each data set. It has to do the context switch. Yeah,
Yes, I agree with you.
yeah. So that's a limitation to doing the code simulation. Yeah. So you have to provide the whole data set comes in, yeah, and do yeah. So that's why the FIFO depth need to be able to accommodate the whole data frame data. Yeah. Otherwise it will hang. For example, in this kernel function, it does a for loop. For example, this kernel function it does a for loop, and then it needs a whole frame of data. Yeah. But in the simulation, the data FIFO is not deep enough to hold the whole data frame. Then you can imagine that this kernel function, when the kernel function executes to halfway, it find out no data input. If there's no data input, then but for this example, use a pointer, right? The FIR. Okay. If you declare the input is an array, for example, your input is an array with the size 128, for example. Okay, if you write the function in this way, then this kernel function will execute 128 data. But however, this host function or the FIFO is not deep enough to hold 128 data. So you can imagine this RTL simulation will hang because no more data fit in. The simulation could not complete. So the simulation hang. Yeah. But in the example, if you use a pointer, then there is no depth. Yeah. So maybe just it's okay. You do the one by one, call the function one by one. Yeah. Okay, so here give you a rough idea how the cosine does, and when the cosine hang, don't be surprised. Yeah, often you try to weight the data. Yeah, or sometimes it's overflow. If this process, if you have a kernel function, two kernel function connected, and the FIFO depth is not enough. Yeah, and then this overflow and this one wait for no data. Or sometimes the kernel function has a feedback path. If there's a feedback path, yeah, if there's a feedback path, it's easily deadlock. Not just for simulation, in actual hardware, it could be deadlock too. Yeah, if you don't properly size your FIFO, the hardware, yeah, the actual hardware will hang, not just the simulation. Yeah, and we will address this issue in the future lecture. Yeah. Okay, so we finish this yeah, the Vitis development flow. Yeah. So I can take questions. Yeah. Do you have any questions? Okay. Yeah. So now this conclude today's course. Yeah. Okay. So hopefully that we can have a lab 3. But actually for lab 3, you can actually run through the Vitis flow. Yeah, if you have the Vitis tool installed, yeah, you can generate the bitstream. The only thing is the last step to upload to the server and run with the FPGA. But that run very fast. But I believe you can still work on the lab 3. Yeah. Okay. Okay, so it's quite late today. Yeah. So if there is no question, then let's call it a day.